Section 7.2, Work and Kinetic Energy. I promised you we'd get right to work, right? All right, so we're going to account for a change in kinetic energy by saying that energy has been transferred to the object or from the object, right? We've either given the object more energy, so it now has more kinetic energy, or we've taken energy out of it, so it has less kinetic energy. If the transfer of energy is done by a force, we say that work is done on the object by the force. So work we use a capital W for. This looks like our weight symbol, which is why I try to avoid using capital W for weight. Work W is energy transferred to or taken from an object by means of a force acting on the object. If the energy is transferred to the object, we say that's positive work, and the energy that's transferred from the object is negative work. Note, this is not the common meaning of work that we use in our everyday life. To do work on an object, there must actually be energy transfer, right? So if I have a ball and I throw it, then I'm doing work on the ball, right? The ball has gained kinetic energy because I did positive work to it. But if I push on an immovable wall, I may put a lot of force into it, but I'm not actually doing any work because the wall hasn't gained any energy. It's still just standing there, not doing much. You may have seen this already on exams. You actually have to write some things down, express thoughts, connect to some of the big ideas in order to get credit. You have to get somewhere with the problem. If you just stare at the page, there's no work that you can get credit for. So you always want to show your work. So work means you need to have some energy transfer. Right, now if we want to derive an equation for how work is related to the force, we can start with our force equation, our favorite, F equals ma. Newton's second law, it shows up yet again. So we'll work in one dimension here for simplicity, and we can also note that we can use that kinematic equation we just saw in the last section. The final speed squared plus is equal to the initial speed squared plus 2 times that acceleration in one dimension times the displacement, d. So if we rearrange into kinetic energies, right, so solving the ax is equal to F divided by m, so we plug that in here, and then we subtract the v0 to the other side, we divide the 1/2 to the other side, and we multiply the m that's in the denominator to the other side. We can rearrange this expression so that the left side is both kinetic energies, right? We have 1/2 mv squared, that would be our final kinetic energy, minus 1/2 mv naught squared, which is our initial kinetic energy. And we know change in kinetic energy is related to the amount of work. So since the left side is the change in energy, the right side is going to be our work. So work in this specific one-dimensional case is the force in the x direction times the displacement in the x direction. This means that to calculate the work a force does on an object, as that object moves through some displacement, we only use the force component that is along that object's displacement. The force component that's perpendicular to the displacement does no work because it's not contributing at all to the motion. Now, this form of the work equation is useful, but again, it's limited to the x direction. So we'd rather have something a little more general. Something that describes how much work is done by a force, depending on how much that force is pushing in the same direction as the displacement or against the displacement. So to do that, we can use our vector knowledge and use the dot product. So this comes from the idea that if we have some force that's at an angle, like so, and the displacement, say, is horizontal, but it doesn't have to be. That's why we don't use an x specifically here. Then if we know the angle between these, and we call that phi, we can figure out how much the force is along that displacement. right? And that would just be the displacement component. So if we make a little triangle there, we could show that this lower piece is F times cosine of phi. And so now we can multiply the amount of force that is along the displacement times the displacement. This is what we did back in the vector chapter with the dot product. So if we're in vector form, the lower equation is easier to use with the dot product, but you can also work with the magnitude of the force times the magnitude of the displacement times cosine of the angle between them. A few notes for these equations. First, the force here must be constant. This isn't a force where it can change in time. We need to have a constant force. The object here also is going to be particle-like. So it's rigid. We aren't worried about rotations or anything weird or wiggly, wobbly, timey-wimey. And then the work can be positive or negative. What? Well, cosine, if you remember, can give us a positive out, or it could give us a negative. When does it give us a negative? Cosine gives a negative when they aren't pointing in the same direction, once the vectors are pointing in opposite directions. So what does this mean? The starred point here gives us a clue. It says a force does positive work when it has a vector component in the same direction as the displacement, and the force does negative work when it has a vector component in the opposite direction. And the force does zero work when it has no such vector component. So if the force is pointing with some component in the same direction as the displacement, that means it's helping the displacement, so it's positive work. If the force is instead pointing against the displacement, that now has, even if it's just a component pointing against it, that's now fighting the displacement of the object. So it's taking energy out of it. And that's why we'd call it negative work. Once again, if the force is completely perpendicular to the displacement, that's not going to do anything in terms of affecting the energy of motion. So that's not going to do any work. Right, work, because it's talking about changes in energy, is going to have the same SI unit as the joule, the same that we have for energy. In the British system, the unit is the foot-pound. We're not going to use that for this class, but you can note it as an example. So here we have an example of a bead on a wire, and a force is applied at this angle relative to the wire. And we can note that when we break that force down into component along the wire versus component perpendicular to the wire, the amount of force perpendicular to the wire is not doing any work. It's not affecting the motion, versus the component force along the wire is doing work because the bead is able to move in that direction along the wire. So you could start out with a small kinetic energy, and if you apply a force in the same direction as the initial velocity, then that force is going to do positive work and increase the kinetic energy. So we have a larger final kinetic energy after some displacement d. We have thus increased things. A couple other notes: if you have two or more forces instead of just a single force, you can find the net work with the sum of the works done by the individual forces. So you can find how much work is done by the pushing force, how much work is done by friction, how much work is done by whatever we may have. Note there are two different methods to calculate the net work here, and I have to try and pause every time I say net work, because it's really easy to just say network and think of internet and connectivity. Instead, it's the net work. So it's the overall amount of work that we have. And the two different methods we have to calculate it: one, we can find all of the individual works from the individual forces and sum those works up. The other method is we can take the vector sum of the forces, F net, and then calculate the net work once from that net force. So either method works out, but it's important to understand both. Now, we said that work is the change in kinetic energy. Now we can write that explicitly as an equation. Probably should have done it sooner, but better late than never, right? This is a really handy equation for solving problems. It says that the change in kinetic energy is equal to the net work done. So the net work here means all of the possible work. So that's why we needed that last slide to explain. It's not just the work done by one force, but the work done on an object by all the forces, which some of the forces may not be doing work, but we want to know for sure. We can write the change in kinetic energy as the final kinetic energy minus the initial kinetic energy. So that gives us another way to write this, that we could say our final kinetic energy is equal to our initial kinetic energy plus whatever work is done. I like this framework because it shows how the work is either adding to the initial kinetic energy to increase the overall kinetic energy for the final, or if the work is negative, it's removing some of that initial kinetic energy. So that I find helpful in thinking about this. And this work kinetic energy theorem, as mentioned, holds true for both positive and negative work. So we do want to pay attention to the signs here. So a couple examples real quick. If the kinetic energy of a particle is initially 5 joules, a net transfer of 2 joules to the particle is positive work, and so the final kinetic energy comes out to 7. If there's a net transfer of 2 joules from the particle, then that's going to be negative work. And so the negative work subtracts 2 joules from the initial 5 joules, and the final kinetic energy is now only 3 joules. We've removed kinetic energy from the system. Right, so with these examples in mind, let's take a look at a checkpoint. So the checkpoint says a particle moves along an x-axis. Does the kinetic energy of the particle increase, decrease, or remain the same if the particle's velocity changes from A, -3 meters per second to -2 meters per second, B, from -2 meters per second to 2 meters per second? C, in each situation, is the work done on the particle positive, negative, or 0? So I want you to think about all 4 parts here, come up with an answer to them, and then we'll check in just a moment. So go ahead and pause the video now. All right, did you do that? Okay, well, let's see. In case A, the velocity changes from -3 meters per second to -2 meters per second. What does that mean for the kinetic energy? Well, that means the initial kinetic energy depends on this -3, but it's squared. Because energy doesn't actually care about what direction you're going. So we have -3 squared versus the final is 1/2 mv times -2 squared. So the negatives are going to disappear with that square. Which one's going to be bigger? The initial kinetic energy is larger than the final because it has more speed, so that means it has more kinetic energy. So what happens to the kinetic energy in A? It's going to decrease. What about in B, when we go from -2 meters per second to +2 meters per second? Well, once again, negative gets squared because we only care about the speed here. So if you're going from a speed of 2 meters per second to a speed of 2 meters per second, it's the same overall kinetic energy. You might have to do work to change the velocity, but the kinetic energy overall, even if it has changed in the middle, is still the same at the beginning and the end, and we're able to focus on those endpoints. So for part B, it's going to stay the same. In each situation, is the work done on the particle positive, negative, or 0? Remember, the work is going to correspond to the change in kinetic energy. So if our kinetic energy decreases, then that's a sign that we have negative work done. What if our kinetic energy doesn't change? Well, then that's a sign that we have no work done. Slacking off. All right, so this hopefully helps. Let's double check our answers here. Click through. There we go. So yes, for A, the energy decreases. C, the energy remains the same. Or part B, the energy remains the same. And part C, the work is negative for A and work is 0 for B. So there we've seen the work energy theorem, right? That we're able to do work when we cause an energy transfer, and that's going to correspond to our change in kinetic energy. So change in kinetic energy is equal to work. And we can calculate work with the dot product of force times displacement.